Hello students, welcome back. We will now continue our discussion on the mathematical foundation of thermodynamics, and I will now introduce to you the difference between exact and inexact differentials. We have already seen that for an exact differential, if there is an expression like m dx plus n dy, I can write it down as an exact differential df provided a particular condition is met. And therefore, for the expression m dx plus n dy, I can write it equal to df or an exact differential provided this condition is met. Now, whenever we talk about differentials, the next concept that immediately comes to our mind is integration of the differential. That is because in real world, we are always dealing with finite changes as the system of interest go from one initial state to the other. And therefore, the exact differential needs to be integrated to find out the net effect of this change. So let us next talk about integration of an exact differential. So for this purpose, I'm still talking about the space spanned by two independent variables, x and y. Then my initial state is characterized by a point where x is equal to xi, I corresponding to the initial point, and y equal to yi. Now, the final point corresponds to x equal to xf and y is equal to yf. Then I would say as x and y values have changed, there will be corresponding change in the value of f, which is a dependent function of x and y. And this change can be obtained by integrating df from the initial state to the final state. We have already seen that this delta f is going to be nothing but the value of f evaluated at the final point where x is equal to xf and y is equal to yf minus the value of f at the initial point where x is equal to xi and y is equal to yi. Now I find that this difference between the new and the old values of x at the final and the initial points, this is equal to integration over m dx plus n dy as the system goes from I to f. As you see, the result of this integration is this, and this result does not depend on the path that we have taken in moving from the point xi yi to xf yf. And therefore, it's very important to note that the value of delta f, that is the change in f of xy as it goes from the initial to the final point, it depends only on the value of fxy at the initial and final points. And it does not depend on the path taken in going from the initial to the final state. This is a hallmark of a differential, that is an exact differential. Now, what happens if I have a closed path? If I have a closed path, then I is equal to f. Then what is delta f? Delta f is going to be equal to f evaluated at xi yi minus once again x evaluated at xi yi, and obviously the result is 0. Now, therefore, if I go from an initial point to another point that is the same as the previous one, this is a closed path. and the integration is then given a sign like this. And as you can see that if f is an if df is an exact differential, the cyclic integral of f is going to be equal to 0. This is pretty simple. And in this background, we come back to the question of an inexact differential. Now, what is an inexact differential? If you have a differential which is of this form, mxy dx plus nxy dy, it is not representative of an exact differential if it so happens that del m del y x is not equal to del n del x y. So let us take an example and see how this happens. So let us focus on this particular form. What kind of function is z? Z is a function of x and y, and then I find that dz is equal to y dx. So if I want to express this differential in this functional form, then what is m? M is the coefficient of dx. So here the coefficient of dx is y. So I write down that m is equal to y. Now, do you see any term dependent on dy in this expression? The answer is no. And therefore, what is the value of n? The value of n is n equal to 0. Therefore, now I have m equal to y and n equal to 0. Do you think del m del y would be equal to del n del x under such condition? Obviously, what is del m del y? Del m del y, keeping x constant, that is equal to 1. And what is del n del x, keeping y constant? Obviously, this is equal to 0. And therefore, if I have a differential dz which is equal to y dx, in spite of the fact that it could be written in a functional form like this, it does not satisfy the condition that del m del y, keeping x constant, is equal to del n del x, keeping y constant. Therefore, for this differential, del m del y x is not equal to del n del x y. And therefore, I would say that dz is not an exact differential, it is an inexact differential. There are other examples as well. Now let us have a look at this particular differential. This is x dy. Now once again, if I want to write dz in terms of m dx plus n dy, what is going to be m? Of course, m is going to be 0 because it is only when m is equal to 0, m dx term will not appear. So m is equal to 0 and n is equal to x. And you can very easily show that here dz is going to be an inexact differential. Similarly, there is another example that I have taken where I find that I have defined another differential dz that in this particular case is a little more complicated one, but still it is possible to find out the m and n values, and then you see that you can, if you do the little bit of algebra required here, you will see that del m del y x is not equal to del n del x y. And once again, therefore, I will say that in all these cases that I have highlighted over here, these are inexact differentials. So I would like you to remember the forms of these two inexact differentials for the purpose of the rest of my discussion. Now we have seen that under such circumstances, we have useful properties for exact differentials. and inexact differentials exist. So are there any useful properties of the inexact differentials? Here I have highlighted one very important property of the inexact differentials, and it says the sum of two inexact differentials can be equal to an exact differential. Now, I will not go into a rigorous mathematical proof of this statement. Rather, for the purpose of understanding the principles of thermodynamics, I will take a simple graphical route. Now, to do that, I will take a first case where I'm thinking about an inexact differential that we have already seen, and this is dz prime is equal to y dx. Please note that for all inexact differentials, I'm not writing them as dz. Rather, I'm using a special symbol del with a cross on the top. So whenever I'm using a notation like this, the message is this is an inexact differential. Now what happens if I integrate this inexact differential? Now integration, as you know, is it corresponds to finding out the area under a curve. Now in this picture, when I integrate from point 1, which is this, to point 2, the function y dx, when can I do the integration? Provided I know y as a function of x. Otherwise, I cannot do this integration. But initially, we started by saying that x and y are independent of each other. Therefore, if z prime is a function of x and y, and dz prime is an inexact differential, in that case, I have to define y as a function of x to find out the value of this integral here. So now let me define this red curve as a functional dependence of y as the system passes from the initial point x1, y1 to the final point x2, y2. And then what is the value of this integral? The value of this integral is then the area under this red curve, which has been marked here as the area 1 and shown using green color. And therefore, I would say that as the system passes from the initial state to the final state, we have chosen to change y from initial point to the final point along this red path that has been highlighted here. I could have chosen some other path. In that case, let us say this was the path I would have chosen. So you understand that the area under this dashed curve will be very different from the area under the solid red curve. And therefore, the answer to my question that what is the result of this integration, I would say that is dependent on the path that you have chosen to go from the initial state to the final state. Now, the second case that we consider here is another inexact differential del z double prime, and that is x dy. So once again, if I integrate dz prime double prime, I understand that I have to choose some other area, some other pathway while I go from the initial path to the final path. So let me choose the same path that I had before. So here, initially, I thought that I'm expressing y as a function of x. Here, I've inverted the problem and varied x as a function of y along the same path, and then the value of the integral is the area 2, which has been shown here using the light purple color. Now, how do I use these two ideas in order to demonstrate the fact that I have mentioned here. I will take another case, which is dz, which is nothing but d of xy. Now, this is an exact differential that goes without saying. Now, if I integrate this exact differential, what is the answer? The answer is x2 y2 minus x1 y1. Now, graphically, what does this area correspond to? This in the xy plane, where x and y, they vary from, this is initial point and this is the final point. This is x1, this is x2, this is y1 and this is y2. Then x2 y2 minus x1 y1 is nothing but the difference in area. First, this big rectangle that is enclosed by the origin y2, the final point, and x2, minus the area of this small rectangle that has been highlighted in white. And therefore, the value of this integral is equal to the yellow area that has been shown in this figure. Now, please remember, along the chosen path, what we had? We had exactly the same area when I added area 1 and area 2. And therefore, my conclusion is integral 1 to 2 dz, that is nothing but integral 1 to 2 dz prime plus 1 to 2 dz double prime. And that gives me this very important result that dz is equal to dz prime plus dz double prime. On the left hand side here, I have an exact differential. And what do I have on the right hand side of this equation? I have a sum of two inexact differentials. So as you see that this is therefore demonstrated by using a very simple graphical representation. Let me go to another very useful property, and it says that multiplication of an inexact differential by an integrating factor can give a product which is equal to an exact differential. So let me take an example once again and explain what I mean. I have already shown to you this example of an inexact differential where this is the m part, this is the n part, and I understand that this is an inexact differential. And here, if I multiply both sides by this integrating factor tau, what do I get? I would get on the left hand side, the term will become dz by y square. And what shall I have on the right hand side? I will have a form something into dx plus something into dy. So now if you check, this is converted to the form of an exact differential. And I can actually write this as a d of this function. So this means that if I define f as this function, then tau into dz, tau, that is the integrating factor, when it multiplies the inexact differential, it converts, the product is an exact differential df. Therefore, multiplication with a suitable integrating factor converts an inexact differential into an exact one. So once again, let me make it very clear that I have not tried to establish these relationships in a rigorous mathematical way. Rather, what I have done is I have taken a simpler route of showing you why these relationships are actually possible if I am dealing with simple functions. Now the question is, in thermodynamics, are these useful? These two results that I have shown to you are indeed useful That is because the mathematical statement of the two important laws of thermodynamics are actually representation of these two mathematical results. Let us have a look at the first law of thermodynamics. The mathematical statement of the first law of thermodynamics is this. So what is du? du is the infinitesimal change in the internal energy of a given system when the system has exchanged dq amount of heat and dw amount of work with its surrounding. Now, you can supply heat to a system, or you can make the system do work only when the system is passing from one state to the other. Therefore, absorption of heat, the differential amount of absorption of heat or differential amount of work done on or by the system appears during the change in state, and they do not have any meaning whatsoever when the system is at equilibrium and it is sitting there, undergoing no change in state. Therefore, it is understood that dq and dw, these two are inexact differentials. But when they are added up, they make up this exact differential. So, while this is physically intuitive, that yes, you can change the internal energy of a system by heating up the system, by placing it in a thermal contact with a thermal reservoir, or you can push the piston down and do some work on the system, or you allow the gas to push the piston up and do some work on the surrounding. These are possible, and these are the two ways in which the internal energy of the system can change. But whenever mathematically you write down this mathematical statement of first law of thermodynamics, immediately an inquisitive student would ask, is this mathematically feasible? You have on the left-hand side an exact differential, and you have on the right-hand side differentials of two quantities which appear only during the change in state across the wall separating the system and the surrounding, and they do not have any meaning as far as definition of the equilibrium state of the system is concerned. And therefore, Q and W are ideal candidates whereby dQ and dW will be an inexact differential. But as we have already demonstrated, this is mathematically feasible because the sum of two inexact differentials can indeed be equal to an exact differential. As we will see in the later part of the course, the mathematical statement of the second law of thermodynamics is this. If dq reversible is the infinitesimal amount of heat exchanged between the system and its surrounding, and if such exchange has taken place reversibly at a temperature T, then dq reversible by T is equal to ds, where S is a thermodynamic function which is a state function, and accordingly ds is an exact differential. This kind of relationship once again is mathematically feasible. Why? That is because multiplication of an inexact differential by an integrating factor can actually be equal to an exact differential. And therefore, the second law of thermodynamics and its mathematical form is also a valid one. Therefore, what we have learned in these lectures is as follows. It says that thermodynamics deals with energy functions or some other macroscopically measurable properties which characterize the equilibrium state of the system. These are called state functions. These state functions, like internal energy, temperature, pressure, etc., they can take up distinct values as the system goes from one initial state to a final state during the change in state. And therefore, if there is an infinitesimal change, there is an exact differential that describes the change in, for example, the internal energy as the temperature changes by an infinitesimal amount. But there are quantities with which we are accustomed to, we have seen them in our experiments like heat and work, which appear at the boundary or the wall separating the system and its surrounding during the change in state. And very small amount of heat exchanged is once again given this notation dq. But dq, is it a state function? The answer is no. Why is that so? That is because the concept of dq is valid only when a change in state is taking place. It is not a quantity that is used to define the equilibrium state of a system. And therefore, the small differential, the differential associated with a quantity like change in heat is an inexact differential. The same considerations apply for the concept of work as well. So in the next lecture, we will examine the different experimental ways in which one can supply heat and what is the consequence of heating up a system or taking out heat from a system or cooling it down, and also the concept of work, and combine the two of them to have a quantitative understanding of the first law of thermodynamics. Thank you.